Welcome to this lesson on direct memory access and the IC 8257, which is a direct memory access controller. In any microprocessor based system, different methods of input output operations are performed. For example, we have the simple parallel IO, the serial IO, the program initiated IO, which is also called the handshaking technique, and the device initiated IO, which is an interrupting technique. All these IO techniques involve the CPU as the central controller, which leads to lot of slowness in the process. When the program initiated IO is used, if the IO device is slow, the CPU has to get into number of wait states. In an interrupting technique, the CPU has to branch to an interrupt service routine before the IO transfer takes place. If large amounts of data are involved in the IO transfer, these delays are going to be large and the entire process will be slowed down when the IO transfer takes place through the CPU. One way of overcoming this difficulty is to isolate the CPU, allow the memory and the IO device to perform the data transfer directly. Such an operation is called direct memory access. Since the CPU is not involved in direct memory access, it requires a separate controller to perform these operations, and this controller is called the direct memory access controller. The direct memory access could be explained with respect to the diagram that you are going to see right now. In this diagram, you see three switches, one each on the address bus, data bus and the control bus. When direct memory access is not performed, these switches are connected such that the microprocessor is connected to the address bus, data bus and the control bus. When direct memory access is desired, the switches are shifted to the other position where you will see the address bus and the control bus getting connected to the DMA controller, while the data bus gets isolated from the CPU and is connected only between the IO and the memory. Such a process is direct memory access. The direct memory access controller could normally work in two modes. One is a slave mode where the CPU and the direct memory access controller interact, while the other one is a master mode where the direct memory access controller connects the memory and the input output device. Whenever a DMA operation is to be performed, the following steps will have to be taken. The IO device which desires direct memory access indicates its intention by giving a request to the direct memory access controller. Having processed this request, the DMA controller indicates to the CPU through the hold signal the intention for direct memory access. The CPU immediately tristates its address bus, data bus and control bus and responds with a hold acknowledge signal to the DMA controller. Having received the hold acknowledge signal, the DMA controller gives a DMA acknowledge to the peripheral device which requested DMA, and then onwards allows the peripheral device to perform data transfer with respect to the memory without using the CPU. Before DMA operation is initiated, the DMA controller will be in a slave mode with respect to the CPU, when the CPU will indicate the starting address of the memory location from which data memory access could take place, the number of bytes for which DMA transfer is permitted and the nature of the transfer, meaning whether it is a transfer from the peripheral to the memory or a transfer from the memory to the peripheral. In order to do all these things smoothly, a particular type of DMA controller is desired. One such controller which is widely used with most of the microprocessors is the Intel 8257 integrated circuit, which is a DMA controller with a 40-pin dual inline package. Now you will see the block diagram of the Intel 8257.
IC 8257 is a programmable 4-channel DMA controller. It consists of the following: 4 DMA channels, control logic to manage data transfer, read-write logic, and data bus buffer.
As we had seen in the block diagram which was just shown to you, there are 4 channels in the 8257 DMA controller. Each channel is connected to a separate input or output device. The connection between the peripheral and the controller has got 2 lines, one line called the DMA request line initiating from the peripheral coming to the controller. A second line, which is active low, is a DMA acknowledge signal which goes out from the corresponding channel to the peripheral device. Whenever a device would like to have direct memory access, it indicates its desire by sending a high signal through the DMA request. Each channel has got 2 16-bit registers in itself. One is the channel address register and the second one is the channel count register. These 2 registers are initially loaded by the CPU when the machine is in a slave mode. The address register contains a 16-bit starting address from which direct memory access starts. After every byte transfer, this address register is incremented by 1. The DMA count register, which is also a 16-bit register, contains a 14-bit count number and a 2-bit code indicating the direction of DMA transfer. The maximum number of bytes that could be transferred in one DMA operation is 2 to the power of 14, which is 16k bytes of information. The number of bytes to be transferred is loaded in the lower 14 bits of this count register when the controller was in the slave mode operation. The 2 higher bits, namely bit 14 and bit 15 of this count register, are given a 2-bit code to tell what is the type of DMA transfer that is desired. If both these bits are 0, the DMA transfer is in what is called a verify mode, where there is physically no transfer taking place, but whatever is in the memory is verified by whatever is available with the peripheral. If the 15th bit is 0 and the 14th bit is 1, it involves a write operation, signifying a transfer from the peripheral device into the memory. If the 15th bit is 1 and the 14th bit is 0, it signifies a read operation, which would mean that the transfer is from the memory to the peripheral device. If both the bits 15 and 14 have got a 1 value, we have an illegal combination and the DMA controller will not perform anything under this condition. You will also find that these 4 channels have got a built-in priority. Most of these controllers have got a built-in priority which can be probably violated under certain conditions, but if the priority of the controller is used in 8257, channel 0 has got the highest priority, channel 1 gets the next higher priority, channel 2 comes next and channel 3 has got the least priority. it is possible to have a rotating priority arranged in which the same order is maintained, but the priority starts with that channel next to the priority channel which just finished DMA. We will see this priority rotation at a later stage after we check some of the other words. The control logic has got two registers, a mode register which is 16-bit long and a status register which is 8-bit long. The mode register will have to be written into by the CPU with the programmer's program, while the status register will have to be read by the CPU. The mode register requires an input operation from the CPU, while the status register requires only an output operation from the CPU. You will now see in the next diagram the formation of the mode word.
Bit D0 enables DMA channel 0. Bit D1 enables DMA channel 1. Bit D2 enables DMA channel 2. Bit D3 enables DMA channel 3. Bit D4 enables rotating priority. Bit D5 enables extended write. Bit D6 enables TC stop. Bit D7 enables auto load.
As we had just seen in the format of the mode set word, the mode set word written into this control logic performs 5 different things. The first thing is it enables or disables individually each of the 4 channels. The second thing, it enables a rotating priority. The third thing, it performs what is called an extended write. A fourth thing, it is capable of doing what is called an auto reloading. And the last thing, when the terminal count in the count register becomes 0, it disables automatically the channel which was enabled by way of priority. We will take each bit individually and try and see what is the operation of that bit. Bit D0 enables channel 0, which means if a 1 level is put inside this bit in the mode set register, channel 0 will be enabled to perform DMA operation whenever it gives a request. If on the other hand a 0 is put there, channel 0 will be disabled, which means even if channel 0 requests DMA operation, the DMA controller will not attend to this particular request. The same thing happens to channel 1 if the bit D1 gets a 1 or a 0 value. Channel 2 is enabled or disabled by putting a 0 or a 1 in bit D2. Channel 3 is enabled or disabled by putting a 1 or a 0 in bit D3. So, the lower nibble of the mode set word is only used to enable or disable one out of the 4 channels available in the DMA controller. Bit D4 is used for rotating priority. The rotating priority is such that channel 0 gets the highest priority and channel 3 gets the lowest priority in the normal course, but at any point of time after a particular channel has finished DMA operation, the priority goes to the next channel in the priority order. For example, suppose channel 0 requested DMA operation and has performed this operation successfully till it was disabled because the terminal count becomes 0. You will find that channel 1 will become the highest priority channel, channel 2 will have the next higher priority, channel 3 will get the third priority, and channel 0 will automatically get the lowest priority. Similarly, if at a particular time channel 2 was performing DMA operation and was disabled because the terminal count is 0, the priority, when the rotating priority is enabled, will become channel 3, channel 0, channel 1, channel 2 in that particular order. This rotating priority is enabled by putting a 1 in bit D4, while a bit 0 in that disables the rotating priority. We also have an extended write facility available in the mode set word, which is done by putting a 1 corresponding to bit D5. An extended write is one where the memory write and the IO write control signals are made available to the memory and the peripheral ahead of time by 1 clock period. Normally, when the control signal gets delayed, the controller gets into a wait state if one of the two devices, either the peripheral or the memory, turns out to be slow acting. One way of overcoming this wait state is to give a memory write and an IO write control signal 1 clock pulse ahead of the operation, so that both the memory and the IO device would know that a write operation is being performed. This extended write facility is made available in the DMA controller by putting a 1 signal corresponding to the bit D5. We have a terminal count enabled bit in bit D6, which when enabled automatically disables the channel performing DMA transfer whenever the terminal count register of that particular channel reaches 0. The initial count, which tells the number of bytes permitted for the transfer, is loaded into the count register. After each DMA transfer, the count register is decremented by 1, and whenever the terminal count in the count register becomes 0, the channel is automatically disabled if the bit D6 in the mode register gets a 1 value. The highest bit in the mode register D7 enables what is called an auto load operation. This auto load function is available only for channel 2. If the channel 2 has to be disabled because the terminal count reached 0, if the auto load has been set, that is, if bit D7 has got a 1 value, the count will be once again loaded into the count register, and a DMA transfer will be permitted for the same number of bytes once again, because the auto load facility is made available in the mode set register. So, the 8-bit combination that we have put in the mode set register gives a lot of variety of operations as far as the DMA controller is concerned. The DMA controller also has a status register where the status will be available to be read by the CPU at any point of time. Now, let us see the status word format.
Bit D0, TC status for channel 0. Bit D1, TC status for channel 1. Bit D2, TC status for channel 2. Bit D3, TC status for channel 3. Bit D4, update flag.
You just saw the status word format. The status register is 8-bit long, but only the lower 5 bits are useful when we program the DMA controller. The status word indicates whether each of the channels is still in a count mode or has reached a terminal count mode. Bit 0 of the status register has a 0 value as long as the terminal count of channel 0 has not been reached, and comes to a 1 value when channel 0 reaches a terminal count. In other words, if the count register in channel 0 is non-zero, the status corresponding to bit 0 will have a 0 value. If the count register of channel 0 gets a 0 value, the bit 0 in the status register will get a 1 value. As far as bit 1 is concerned, it indicates the terminal count of channel 1 in the same form. Bit 2 indicates the terminal count of channel 2, and bit 3 indicates the terminal count of channel 3. So, the lower nibble in the status word indicates whether each of the 4 channels have reached the terminal count or not. Bit 4, which is the 5th bit from the lower side, contains an update flag which will have to be set if we want to use the auto reload mode. If the auto reload mode is desired on channel 2, where the count register will be reloaded with the count and DMA transfer will be continued for channel 2, the update flag will contain a 1 value in the status format. So, the status format is only for the CPU to read back and find out what is the status of the DMA controller. The address registers, the count registers and the mode or status register have got certain address combinations which is uniquely defined by the lower 4 bits on the address bus. Bits A3, A2, A1 and A0 have different combinations for different registers in the DMA controller. Now, you will see a diagram which will give you the various address combinations.
Address 0000 is used for channel 0 DMA address register. Address 0001 is used for channel 0 terminal count register. Address 0010 is used for channel 1 DMA address register. Address 0011 is used for channel 1 terminal count register. Address 0100 is used for channel 2 DMA address register. Address 0101 is used for channel 2 terminal count register. Address 0110 is used for channel 3 DMA address register. Address 0111 is used for channel 3 terminal count register. Address 1000 is used to write the mode set register and to read the status register. That is, address 1000 along with write control signal enables mode set register and along with read control signal enables status register.
Having seen this diagram, you will now see the interfacing arrangement for the various lines in the DMA controller when the DMA controller is working in a slave mode. In this diagram, we have assumed an I/O map such that the DMA controller has got its registers addressed from 70 to 7F. Therefore, the DMA controller is selected with the hexadecimal digit 7 corresponding to the address lines on A4, A5, A6 and A7. In other words, if the address on A7 is 0, the address on A6 is 1, A5 is 1, A4 is 1, this particular DMA controller will be selected by the I/O map with addresses A3, A2, A1, A0 representing the various registers inside this DMA controller. The I/O read and the I/O write lines in this diagram are connected to the I/O read, I/O write control lines on the control bus. The address lines will be varied depending on the software program that the user has to write in order to load the various numbers into the various registers. The lower 4-bit combination for A3, A2, A1, A0 where all 4 are going to be zeros indicates the address register of channel 0. A 0001 on the lower 4 bits indicates the count register of channel 0. A combination 1000 for A3 to A0 is going to indicate the mode register when we are going to output operation into the DMA controller from the CPU. Now, let us assume that we are going to use channel 0 for DMA operation and we are going to transfer data from an input device into the memory using this channel 0. You will see the software program that the user will have to write in order to achieve this particular DMA operation. Now, referring to this program, you will find the first instruction is move immediate into the accumulator and number 41, and the second instruction is out 78. 78 is the address of the mode register inside the DMA controller which we selected in the previous interface diagram. Now, the bit D0 is made 1 so as to enable the channel 0, and bit D6 is made 1 so as to enable the terminal count stop bit. So, the number 41 just indicates that channel 0 is enabled and the terminal count is enabled, which means channel 0 should stop whenever the count register becomes terminally 0. The next instruction is move immediate A64. 64 is a hexadecimal number standing for the decimal number 100, which indicates that 100 bytes of data are going to be transferred using channel 0. This is outputted into 71. 71 is the address of the terminal count register corresponding to channel 0. The next pair of instructions, move immediate into the accumulator 80, out 71 indicates the most significant byte of the count register to be loaded from the microprocessor using the number 80. The leading 1 in this 80 indicates the direction in which data has to be transferred, while the lower 6 bits do not modify the count number as such. Having loaded the count register, we will have to give the starting address, which we are assuming is 1000 hexadecimally, and we are using 4 instructions: move immediate A00, out 70, move immediate A10, out 70. 1000 is the starting address from which DMA transfer is going to take place in the memory using the peripheral connected to channel 0. So, this program clearly illustrates how the processor is initializing the DMA controller in the slave mode operation. You are now looking at the connection diagram when 8257 is working in a master mode operation. The master mode starts whenever the DMA controller gives a hold signal to the CPU and receives a hold acknowledge from the CPU. Once the master mode operation starts, the data lines D0 to D7 are used to transfer the higher 8 bits of the address lines. In other words, D0 takes the place of A8, D1 gets A9 and so on till D7 finds itself holding the A15 control signal. A3 to A0, which was used for addressing the various registers, now holds the lower nibble of the memory address. So, A7 to A0 hold the lower 8 bits of the memory address, while D7 to D0 hold the higher byte of the memory address. The IO read and the IO write control signals now change in their direction and are connected to the peripheral device to indicate whether a read or a write operation is initiated from the peripheral. The memory read and the memory write control signal are given to the various memory units, so that each memory unit will decode these lines and find out whether the memory has to perform a read operation or a write operation. In addition to this, there are 2 other control signals involved in the master mode operation. One control signal is called the AEN or the address enable control signal, which is active whenever the 16-bit memory address is on the lines A0 to A7 and D0 to D7 of the DMA controller. A second control signal is what is called the address strobe control signal, which is made active whenever the DMA controller wants the memory units to latch the address information available on A0 to A7 and D0 to D7. Another important aspect to be noted when the DMA controller works in master mode is that the DMA request from a particular channel should remain high if it requires block transfer as long as the terminal count becomes 0. If on the other hand the DMA request becomes inactive when the acknowledge is given to the channel, the transfer will stop with a single byte of information. Having seen the significant aspects of the 8257 DMA controller, we will conclude this lesson by just mentioning that there is a more superior DMA controller with an IC number 8237, which normally finds its place in the IBM personal computer. The main difference between the 8257 and the 8237 is that the 8237 has got a 16-bit count register, which enables a total count of 64K, thereby permitting a block transfer of 64K bytes of information. 8257 on the other hand has got only a 14-bit count, which means one channel at one point of time will be able to transfer only a maximum of 16 kilobytes of information. We hope you enjoyed this lesson and will cherish the memories of this classroom in the days to come. Thank you.